Good day, everyone. My name is Michael Lüken. I'm one of the co-organizers of the IEEE second presentation series on nuclear energy. Welcome to you all. Today, we have a presentation on the developments in Ontario, talking about advancing clean energy, Ontario's Darlington new nuclear project, and the BWRX 300 small modular reactor. So I welcome Michael Takla. He's a PEng and is working as an engineering manager at Ontario Power Generation, and of course that is in Canada. And now it appears I have an issue in my slide, doesn't want to move forward. Let me find it. There we go. Okay, so why do we have this presentation series? Let's talk about that. In 2014, Ban Ki-moon, then the Secretary General of the UN, essentially stated that energy is the golden thread that connects economic growth, increased social equity, and a healthy environment. Sustainable development is not possible without sustainable energy. And of course, with that, we do need a global energy systems transformation. And as has been recognized more and more in recent years, and particularly the last couple of years, is nuclear power generation is part of the energy systems transformation. So a number of different groups within IEEE got together to start the first series, presentation series on nuclear energy last year. Vancouver section was the lead to start with. Future directions, the IEEE SESTEC initiative, the IEEE NPSS, the Society, IEEE Standards Association, and IEEE Planet Positive 2030. And the purpose really is for this presentation series on nuclear energy to essentially address a large, broad audience, not just the engineering and technical community. So we are hoping to reach industry, regulators, policymakers, community stakeholders, and so on. So it's for the general community with an interest in the energy transition, clean energy and energy alternatives, and of course, nuclear reactor technologies and related topics. So it is to serve the needs of the profession and the public by increasing awareness and understanding of nuclear technologies. We do have a few links for you. The web pages about the presentation series, the access to the presentation series, the a mailing list that you may want to join for upcoming presentations, etc., and the past presentations that are available on demand. Essentially, all presentations except we had one presentation of the movie Nuclear Now. All other webinars are available on demand for you to see, and here is the link. So let me spend a couple of words on the next presentation that is going to happen later in April, and that is going to be presented by Dr. Karen Stevenson of McMaster University. She is a Canadian expert in nuclear research and education, and she is the Director of Nuclear Research and Education Support at McMaster University. So she will be talking about nuclear at McMaster, seeing as the activities at McMaster universities are moving from 24/5, like 24 hours, 5 days, in 24 and moving to 24/7 in 2027. The McMaster nuclear reactor is the largest such research reactor in Canada and provides a very extensive platform for research and education, but also nuclear isotopes for medical applications. And so both the research highlights and the growth of outreach and education activities will be shared in that presentation. Now to today. So today we welcome Michael Takla, and he's going to give us an update on the Darlington new nuclear project, the first of its kind in the G7. So Michael Takla serves as the owner's engineering manager for units 2 through 4 of the Darlington new nuclear project, of course, of Ontario Power Generation. And in this role, he provides leadership and oversight for the design, procurement, and construction phases that are associated with the licensing and development of units 2, 3, and 4, as well as common site infrastructure. And prior to this position, Michael has specialized in regulatory compliance, focusing on grid site regulations in alignment with NERC and NPCC standards. His engineering expertise also encompasses the experience in managing the main power output systems and grid connection projects for the DNP. And he has contributed to the development of the SMR, Small Modular Reactor, revision of the IAEA Nuclear Energy Series publication, electric grid reliability and interface with nuclear power plants. So a very varied and a great background. And so Michael Takla is so going to talk about this project that is at the forefront of deploying small modular reactor technology in Canada. It's anchored by the GE Vernova Hitachi BWX 300. And it is North America's first commercial grid-scale SMR project, and the plans are for up to 4 units totaling 1,200 megawatts. The project introduces advanced safety features, including natural circulation cooling, integral isolation valves, and passive heat removal, while at the same time supporting thousands of jobs and boosting Ontario's economy. With that, I would like to welcome Michael Takla and stop my share. So Michael, please take over the screen, and the floor is yours.
Thank you so much. Thank you for the kind introduction, and thank you for everyone for the opportunity to be with you all today, to be with the IEEE and all the members and attendees. It's a great pleasure. So I will now share my screen. Just make sure I get the right one.
And just for everybody's reference, Michael Takla is also an IEEE member.
Perfect. Thank you. Can you see my screen now?
Yes, it's there now.
Perfect. Yeah, so thank you. Just already thank you for the introduction there. But yes, I'm with OPG, Owner's Engineering Manager, working on units 2 to 4. I've been with the Darlington New Nuclear Project since 2021, looking after some of the electrical systems and grid connection as part of Unit 1. But recently we started to prepare for the preparing the infrastructure and some of the licensing work and work for units 2 to 4. So we're starting up a team to prepare that work, but we'll get into that here. Perfect. Okay. So SMR is in the Darlington New Nuclear Project, and we'll be referring to that as probably DNNP, just for time's sake going forward. So our agenda today, I would just break it up into 3 parts. First, I'd like to introduce OPG. Some of us might be familiar with it, but I'll give maybe some information and background, and then we'll get into the Darlington New Nuclear Project, how it's been structured, and some highlights, and then I'll get into some aspects of the BWX 300 technology, which is the GE Vernova Hitachi SMR. So who is OPG? OPG is the largest clean, low-carbon power generator in Ontario with a diverse generating portfolio. OPG owns and operates 66 hydroelectric stations and 2 nuclear stations, 2 thermal generating stations, as well as 1 solar facility and 1 biomass facility. and they also operate 4 natural gas-fired generating stations. OPG invests millions in local economies and employ thousands of people to maintain a modern and sophisticated energy fleet. OPG partners with local and environmental indigenous groups to improve the well-being of all of our sites and stations and river systems and communities. For our purposes, so for other nuclear assets on within OPG's portfolio, there is a Pickering Nuclear Generating Station and a Darlington Nuclear Generating Station. In 2020, OPG introduced its first climate change plan, where with the goal of becoming a net zero carbon company by 2040 by balancing the carbon emitted with the amount removed or reduced from the atmosphere, and while helping the markets it serves reach a net zero carbon economy by 2050, and by being leaders in innovation and by leaders in this field. So the IESO, so the Independent Electric System Operator in Ontario, so our system operator, on a yearly basis produces an annual planning outlook looking at the next year. So in October 2024, the ISO released a 2025 demand forecast, a key part of the annual planning outlook. And the new APO projected a 75% increase in electricity demands, going from 154 terawatt hours in 2025 to 262 terawatt hours by 2050, which is about a 60% increase from what was initially planned in the outlook the year before. The primary factors for driving this increased demand are growth in data centers and industrial sector. Secondary drivers include population growth, commercial sector growth, and anticipated electrification of existing facilities. So taking in our climate change goals as well as electricity growth requires or guides OPG into looking for new ways to provide this energy security. And OPG believes SMR, small modular reactors, will strengthen Canada's energy security by advancing nuclear energy and reinforcing the national nuclear supply chain. It also positions Canada as a leader in both large and small nuclear developments while diversifying the energy mix to support and complement other generation series. I'm sure in this type of series, small modular reactors come up a lot, and maybe the different kinds. But just to quickly summarize, there are 3 that you can consider. So there's on-grid SMRs that can go up to 300 megawatts or maybe even a little bit more, with the purpose of providing reliable baseload power and displace coal-fired generation. And those we believe are in near-term deployment, just like our project. There are advanced reactors, 10 to 15 megawatt electric with a 10 to 15 megawatt electrical supply, and really seek to support some heavy industrial applications. And those could be deployed up until the mid 2030s. Where off-grid SMRs in the 1 to 10 megawatt electrical range can be more ideal for industrial and off-grid communities. So we are today talking about the Darlington New Nuclear Project, which is an on-grid SMR. And a target of 4 SMRs. But before we got into that, I think it's good to highlight a lot of the work that was done before that in selecting a technology. So starting in 2018, OPG undertook a high-level review of nuclear technologies and SMRs to identify those with the right size and technological readiness, and those that made sense for Canada for further consideration. So OPG had scanned the market and found about 150 new reactor technologies being developed, but some just weren't credible or appropriate for Ontario and specifically our Darlington site. So it was narrowed down to a top 10 list with medium, high technology readiness levels and credibility to meet our project objectives. In 2020, OPG invited 7 SMR developers to do a due diligence process whereby we went through a much deeper review involving experts from OPG, peer utilities like Bruce Power, Sask Power, or TVA, Tennessee Valley Authority in the United States. And they identified 4 technologies that warranted additional detailed work and 3 to actively work with. before the end of 2020, OPG announced it had begun project planning for Darlington New Nuclear Project for a possible SMR at the site and identified 3 leading contenders, which were GE, Hitachi, Terrestrial Energy Inc., and X Energy. And then it was in December 2021, after working with those 3 companies, that OPG selected GE Vernova or GE Hitachi with the BWRX 300. So this was more than just an RFP where you maybe kind of provide a proposal. We worked with 3 of these vendors as if they were going to be the SMR of choice, and how to make their and work towards like initial designs to make their technology work or in our site. And after that, our effort is when we selected the BWRX 300. This is just a brief review of our timeline here, but I think we'll touch on some of these factors later. But as of now, just to highlight, these are the 3 main licenses that you work through, or sorry, there's more, there's 4 licenses here that you work with getting approval from the Canadian Nuclear Safety Commission, the CNSC. So OPG did receive a license to prepare the site. In April 2025, OPG received the license to construct. So construction has begun in April 2025. And then we have just submitted our license to operate actually like this week. So I'll touch on that later. So it is a very exciting time for us right now. But just wanted to highlight here again, these were some of the methodologies for the technology selection. So the process and methodologies OPG developed were reviewed by an independent expert body called the New Nuclear Review Board. And they found that the process was sound and there was sufficient information to make a sound decision. And OPG structured the assessment process into these 11 areas shown here. So these are the environmental assessment, compliance. So OPG already had an environmental assessment for the site. So how well does this technology fit into that environmental assessment? Project management, design progress and readiness, safety case, fuel supply and security, nuclear materials used, fuel management, any licensing risks, financial review, economic development potential, and opportunities for Indigenous communities, and contractual agreements in the business case. So with the selection of the GE Vernova BWRX and the project initiating, we saw here an innovative project delivery model. So structure around this integrated project agreement, or IPA. This agreement represents an innovative contracting approach for a nuclear project. Under the terms of agreement, GVH Hitachi, who is the technology developer, Atkins Realis, the architect engineer, Aecon Kiewit nuclear partners, who are the construction, and OPG, they provide a diverse range of expertise and services as part of this model. Based on operational experiences, owner-led collaboration is critical to the success of large, complex projects such as DNNP, which builds on OPG's success of the one-team approach, which was used on the Darlington refurbishment. In this approach, the project seeks kind of the best athlete for certain roles or responsibilities. So just to add to what I was saying, OPG is the license holder, maintains overall responsibility for the project, including operator training, commissioning, Indigenous engagement, stakeholder outreach, and oversight. GE Vernova Hitachi is the technology developer responsible for design, procurement of major components, and engineering, and additional support. Atkins Realis, the architect engineer, provides design, engineering, and procurement support, and Aecon Kiewit, the constructor, will provide construction planning and execution. So a fleet approach here is in kind of explaining my role as supporting the units 2 to 4. So the Ontario government is working with OPG to commence the planning and licensing for the 3 additional small modular reactors for a total of 4 SMRs on the Darlington nuclear site. And once deployed, these 4 units would produce a total 1,200 megawatts of electricity, equivalent to powering 1.2 million homes, and helping to meet the increasing demand from electrification and fuel the province's economic growth, as mentioned earlier on. So site preparation, as mentioned, there was a license to prepare the site, and that comes with also a lot of work. So in February 2024, ES Fox completed their early site preparation work at the Darlington nuclear site, which included construction of temporary roads, site grading, and laydown areas installed for stormwater features, establishment of on-site utility. Following the completion of the 2024 site establishment work, the project became ready for nuclear construction work to begin in early 2025. And then on the licensing angle, there was a two-part regulatory hearing to review OPG's license to construct application for the first SMR unit, which were wrapped up in January 2025. And like I mentioned, the license to construct from CNSC was obtained April 2025. And we've been we've been doing some construction since then, but there was certain hold points on certain types of construction. So I'll speak to that later. People are always interested in the financial side, so we'll share a little bit about this. So on May 8th, May 8th, 2025, so last year, the province of Ontario approved the OPG to begin construction on the first of 4 SMR units. This represents the first new nuclear build in Ontario in more than 3 decades. Our current estimate for the project, or the Darlington New Nuclear Project, is $20.9 billion. And OPG and the project partners will further refine this estimate as we complete detailed engineering through definition phases for units 2 to 4 and experiences gained from the first unit's construction. For the first unit, there have been approval for $6.1 billion plus $1.6 billion for systems and services that will be common for all 4 units of the SMR plant. So that includes roads, sewers, bridges, ancillary buildings, fiber lines, tunnels for cooling water supplies, for a total approved budget of 7.7 billion. So that's the first unit and some of the common site infrastructure. The approved budget there represents the release quality estimate for the first unit and common costs. OPG is expecting unit over unit costs to decrease as we apply greater modularity and lessons learned from building the first unit. These are the same practices or project management practices and techniques that were used in the $12.8 billion Darlington refurbishment project, which was completed earlier this year as well, on time and on budget. Good to note, on October 23rd, 2025, Prime Minister Carney and Ontario Premier Doug Ford visited the Darlington Energy Complex to announce an equity commitment to finance the DNNP through the Canadian Growth Fund and the Building Ontario Fund. Through this agreement, the Canada Growth Fund and Building Ontario Fund invested up to $2 billion and $1 billion respectively, each taking minority ownership positions in a project. So just wanted to stop here and just highlight some of the benefits to Ontario and some of the supply chain highlights that are local to Ontario for this project. So for example, ES Fox, as mentioned, is undertaking site preparation work that was valued at about $32 million, resulting in approximately 100 new jobs for Ontarians. BWXT Canada secured manufacturing contracts to support both the Pickering refurbishment and the Darlington New Nuclear Project. And these projects valued at approximately $960 million over 7 years and are expected to generate over 250 new highly skilled jobs, some mainly in the Kitchener-Waterloo region. BWXT is also in the process of negotiating further agreements for units across Canada and the US, and also signed a letter of intent with OSGE in Poland for the first 10 reactors, or the RPVs, reactor pressure vessels, from the Cambridge facility in Ontario. Flow Technology as well as the first Ontario-based manufacturer of nuclear qualified pumps supporting both the SMR project and existing OPG nuclear operations, has committed to expanding its Burlington facility. This expansion is expected to also help create more jobs and employment in the Halton region. So those are just kind of some of the bigger, some of the contracts that will result in economic growth in Ontario. Additionally, some comments on the fuel supply chain. Sorry about the slide messiness there, but OPG has initiated 4 contracts. So one with Cameco, so Canadian company Cameco, which has uranium mines in Saskatchewan and uranium hexafluoride conversion facility in Port Hope, will supply the uranium hexafluoride or UF6. Urenco, so is a US-based company, will provide uranium enrichment services from their operations in New Mexico. An additional contract with France's Orano will provide additional enriched uranium product or EUP from their operations in France. I think this helps create some diversity in your avenues for fuel supply chain. And finally, US-based Global Nuclear Fuel Americas, or GNF, is a GE-led venture that will provide fuel fabrication and related technical services and fuel assemblies. So now just to show some pictures, and we'll show some now and some later, of the Darlington nuclear site. So we are in active construction zone. The site is very active as we are in execution of Unit 1. So starting at the back there, the on-site fabrication building will transform the reactor building modular panels, which are shipped to site, into larger sub-assemblies. The sub-assemblies will then be transported from the fabrication building to the pre-assembly structure. So that's the closer to the screen here, the white tented facility. The sorry, the sub-assembly, the pre-assembly adjacent to the reactor building. So where you see the pre-assembly building here, this is the reactor building shaft. The modules will then be lifted and placed into the reactor building shaft, where they will be installed and joined together. Both the fabrication building and the pre-assembly structure are critical links in our supply chain, ensuring the fabrication and assembly of components meet the highest standard of safety, reliability, and regulatory compliance. The unique part of the pre-assembly building is that it does have the ability to slide. The roof of this is able to slide to allow for a crane to lift off components of the reactor building and place them in the shaft. And it allows it to be closed, obviously, to kind of improve workmanship so that they're not affected by weather. The launch shaft, as shown at the bottom of the screen, is both the location where the tunnel boring machine will launch from, and also will ultimately be the discharge structure. After we excavate the launch shaft down to a certain depth, there will be drilling and blasting before the tunnel boring machine begins tunneling out to the lake. The boring machine will complete a full loop cooling water tunnel out into the lake tunnel, tunneling both deep water intake and the diffusion tunnel. Once the boring machine has completed the full loop, the back loop will be abandoned and isolated to effectively maintain 2 tunnels, one for water intake and one for diffusion. In the back on the east side there, the 4-bay shaft will house the condenser cooling water pumps, which will pump cooling water to all 4 units. And last thing, I think our tunnel boring machine, they'll have names, and I think ours is named after Harriet Brooks. And that should be something that launches later this year in the summer. So a little bit about the BWR. So boiling water reactor are inherently simple, the simplest way to make steam across multiple nuclear technologies. And they're considered a direct cycle system, meaning the steam is generated in the unit that creates the heat, and the secondary system, like a steam generator, is not required to ultimately produce the necessary steam. So water in the reactor vessel, water flows over the fuel, and it's both the coolant and the moderator, slowing down the neutrons sufficiently so that they can be captured by the uranium-235 isotope. And when the U-235 captures a neutron, fission occurs and releases extreme amounts of energy, and the energy boils the water, creating steam under pressure and sending the steam to the turbine generator. I'll just kind of pass through this, and just wanted to, before we get into maybe more of the technology side, wanted to touch base on the licensing status. So in terms of in Canada, OPG has received a license to construct, as I mentioned, in April 2025, and the pre-operational safety analysis report and license to operate report are in development and actually have been submitted. Now they are with the CNSC. In the United States, GE Vernova Hitachi is using licensing topical reports to de-risk areas with lower certainty by obtaining early approvals and enabling technologies. And a construction permit application was filed in May 2025, accepted for review with an expected decision timeframe of December 2026. There has also been engagement with the VGV Hitachi BWX 300 as well in the UK, in Poland, in Czech Republic, in Finland and Sweden, with a lot of pre-engineering assessments and regulatory discussions. So the BWX 300 is a 300 megawatt electrical water-cooled small modular reactor that uses natural circulation and is positioned as the 10th generation of the boiling water reactor family. The design is not a clean sheet concept. It's actually an evolution from the ESBWR, the Economic Simplified Boiling Water Reactor, which has been licensed by the US NRC, a Nuclear Regulatory Commission, and that heritage is used to aim to anchor the technical and licensing maturity of the approach. The stated objective is to deliver clean and flexible energy that is cost competitive with natural gas fired generation. Flexibility is part of the value proposition with load following capability across the 50 to 100% power range. In addition to traditional baseload operation, it highlights non-electric applications, hydrogen production, district heating, and other process heat uses. Now, I will say for the DNNP, we have not pursued hydrogen production or district heating as part of our application. Our target is baseload generation. BWR technology began in the 1950s and matured through early demonstration and first commercial plants, then expanded internationally. Early design changes focused on increasing power density and overall output, while later generations emphasized simplification and standardization based on operating experience and manufacturing improvements. Reactor system simplification is described as a progression from more complex steam cycle arrangements to designs that eliminated external steam drums by using internal steam separators and steam dryers, supported by reactor water cleanup to manage the impurities. Recirculation configurations also evolved significantly towards simplicity in their designs as they progressed over several years. Containment design is also described as evolving from early dry containments to pressure suppression containments in several configurations, with later designs refining geometry and size as systems were simplified. The BWX returns to a dry containment concept, managing reactor pressure with isolation condensers and removing the need for suppression pool. Okay, so to talk a little bit about the safety approach here. So this image tries to capture a lot of information about the strategy, but the safety approach implements the IAEA design and fundamental safety principles with the explicit objective of reducing radiation dose and lowering the probability of early or large releases beyond the plant or the site boundary. Defense in depth is applied using multiple protective layers. First, robust physical barriers, fuel cladding, the reactor coolant pressure boundary, and containment. And second, the features, functions, and practices that reduce challenges to those barriers and preserve their integrity if a barrier is compromised. Across these states, the design is anchored on three fundamental safety functions: controlling reactivity, removing heat from the fuel in the reactor and during storage, and confining radioactive material with shielding and controlled releases. These are mapped in the defense lines DL1 through DL5, and the mitigating functions are safety categorized: safety class 1, safety class 2, and safety class 3, or safety class none, based on the defense line that they support. With emphasis on independence, the diversity passive response for key accident mitigation, probabilistic risk assessment, informed design choices, and digital INC quality and diversity to defend against common cause failures. So a lot of the ways we understand is after gathering all the incidents and risks is understanding the defense lines in place and the functions of those defense lines. And then when you look at your systems components or structures, you look at the defense lines that they participate in or they're required for, and you assign a safety class to that piece of equipment. So this is the plant overview overall. We'll get into maybe some of the highlights of this of the overview here, but just wanted to give a chance to everybody to have a look. So just a little about the nuclear boiler system. So it's the integrated set of reactor side systems that produce and deliver steam, receive feed water, and provide the reactor side functions needed to support safe power operation. It includes the reactor pressure vessel, the main steam system, the nuclear boiler instrumentation, and it leverages the proven design elements from the ABWR, the Advanced Boiling Water Reactor, and the ESBWR. Functionally, the system transfers steam from the reactor pressure vessel, the RPV, to the turbine side and returns feed water to the vessel. It also provides overpressure protection of the reactor coolant pressure boundary, supports the core and the control rod structures, and establishes the natural circulation flow path used for the core cooling. For loss of coolant accident mitigation, the design emphasizes inherent margins rather than adding complexity. That's the overall strategy. So a large water reservoir above the core, a tall chimney volume supporting the natural circulation, and a reduced number and size of vessel nozzles. A key element is placing reactor isolation valves close to the vessel and above the active fuel region to support isolation of breaks and reduce the severity of a loss of inventory events. The reactor pressure vessel itself is a tall vertical cylindrical vessel with a removable head to support refueling and maintenance. Its geometry is a deliberate enabler for that natural circulation feature, with internal structures arranged to support the core, guide and position control rods, and provide the flow and separation path from two-phase mixture to high-quality steam. So above here, we're trying to show some of the arrangements of the fuel bundles, and it's kind of a cutaway of the reactor core itself, um, with positions showing of where the control rods actually would be fitting in. This also lower here is a cutaway of the actual reactor building. So focusing on the RPV central part is your pedestal, your control rods, the core, the reactor pressure vessel overall. And outside of this is your steel plate composite containment vessel, or SCCV, which is within the reactor building. So I'll show that in a second. Or we showed that earlier, sorry. But and then here are the pools above, the reactor cavity pools. Beyond the reactor pressure vessel itself, the nuclear steam supply system includes the steam path, reactivity control hardware, passive heat removal, and the containment and its supporting cooling functions. The main steam subsystem routes steam from the outboard isolation boundary to the turbine stop valves and includes containment isolation valves that close fast and fail closed to prevent unfiltered releases during events, flow restrictors at the vessel nozzles limit discharge during a main steamline break, and steamline drains manage condensate during startup and low load conditions. Turbine bypass valves protect pressure control by routing steam to the main condenser when the turbine demand is low. Reactivity control is provided by fine motion control rod drive mechanisms mounted in the vessel bottom head. I think we showed that earlier. And the associated hydraulic control units provide an accumulator driven scram capability and purge functions. And the control rod drive's hydraulic subsystem provides the required demineralized water supplies to support scram readiness and other related uses. Now, for nuclear instrumentation, the BWX300's in-core measurement approaches uses three complementary detector types. So the LPRMs, or local power range monitor, provide local neutron flux-based power indication through 13 instrument strings, divided into three redundant divisions for broad coverage. Gamma thermometers are add a fully diverse measurement by converting gamma flux into electrical signals and are densely distributed alongside the LPRMs. And the wide range neutron monitors provide wide range neutron monitoring from startup through full power, transitioning from pulse counting at low power to a proportional analog signal as power increases. Here's just an image of the isolation condenser system that provides that passive, high reliability decay heat removal when the plant is isolated and the main condenser can't reject the heat. So it uses three independent trains, each condensing reactor steam in the pool submerged heat exchangers. So you can see here there's three different sets of heat exchangers that are located within the pools above the RPV. Um, and they're meant to return the condensate back to the reactor in a closed loop with natural circulation, and driven by the elevation and gravity. One train addresses the operational upsets, while two trains support a loss of coolant accident mitigation and can sustain decay heat removal for 7 days without operator action. For more extreme scenarios, all three trains are accredited and the above ground unpressurized pools can be topped up indefinitely using simple transportable water resources. And sorry, this is some of the images of the reactor building cutaway. Um, there'll be different items kind of as you proceed. So under this is our base mat foundation, and I'll speak to that a little bit today because that's a major milestone the project has reached, where we've completed the base mat, but now it actually needs to be loaded into the reactor building shaft. But in the building, in the lower levels, we'll have our fine motion control rod drives, and then hydraulic controls, as well as some of our distributed controls and information system, INC systems up here. And as you move up, we'll have different kind of equipment, some fire protection equipment, and DC battery systems as well. So the plant, we mentioned GNF2, but the plant uses a 240 bundle core with GNF2 fuel. So that's GNF is the manufacturer, and GNF2 is the specific type of fuel for this type of BWR. And it was chosen specifically to support natural circulation while keeping the BWR mechanical design for fuel and control rods consistent to reduce risk. Each assembly combines a rod bundle with a Zirc alloy channel that shapes coolant flow and guides control rods, and the lattice design choice supports both stability and load falling flexibility. Refueling relies on established BWR methods using a dedicated refueling platform with multiple features to prevent mishandling, and on-site pool storage is sized well beyond a full core while maintaining conservative subcriticality and cooling margins, with dry cask storage as the long-term option. Planning assumptions include short refueling outages, flexible cycle lengths, and periodic longer inspection outages for major equipment and in-service inspections. So I won't go into all the details on the steam and power conversion here, but can possibly look into answering some questions about that. But I would just like to point out that the generator that our generator system has a gross output of 327 megawatts electrical. That's gross output there. And the pursuit here was to seek out kind of a generator turbine package that can be considered more standard and is common across different types of energy sources, so such as gas-fired plants and something similar to what they would use. So in regards to INC, so the Distributed Control and Information System, DCIS, provides plant monitoring, control, as well as alarms, recording and operator interfaces in both the main and secondary control rooms. The design aligns hardware safety classifications with the plant defense and depth reliability goals. So that's safety class 1, 2, and 3 systems. And you could see that here on this diagram, which kind of shows the different INC systems, and they'll each have like a safety class 1, 2, and 3, or a defense line 1, 2, 3, depending on what they actually support. And that's how you know the maybe criticality of each INC system. The design aligns hardware safety class, the platform selection is tiered by the safety class. So that's what helps us select the right platform. So NUMAC is selected for its for the highest safety class 1 systems. The Mark 6 ES, Mark 6 ES, sorry, Mark 6S, Mark 6 ES, selected for mid-level safety functions, and the Mark 6E without the X is used for some lower safety class systems or safety class none systems. A key protection measure um, feature is the 3-division architecture using 2 out of 3 trip logic to ensure the required trips occur while minimizing spurious trips. And the Mark 6 controller family supports real-time automation with robust configuration and diagnostics, and I think they have a history of being used in BWR plants. A little bit about the control room. So the MCR, the main control building, is in the main control room is in the control building, and it's the primary place where operators run and monitor the plant across all operational and event conditions. Because safety and human factors analysis can drive the need for alternate control location, the design includes a secondary control room, which is in the reactor building. So if the MCR becomes uninhabitable or its functionality significantly degraded, staff can safely transition using paths sized for minimal staffing to the SCR, the secondary control room. The safety class control, the SCR is not meant to operate the plant. Its purpose is to place and hold the plant in a safe shutdown condition. As part of this as well, I think OPG has had to work on building a simulator similar to the MCR to prepare our operators in time for our commercial connection to the grid. This is a single line diagram represents the electrical distribution system as an integrated architecture that both powers the plant loads and provides electrical path from the generator to the grid. You can see also here different defense lines and safety classes highlighted on different systems or different sections of the electrical distribution system. It's segmented by safety class and defense line. There's 3 safety class segments plus a non-safety class segment for the electrical. Under normal conditions, the plant is supplied from offsite preferred power with clear provisions for a loss of offsite power source. For more severe scenarios, such as a total loss of offsite power, the design adds on 2 redundant standby diesel generators and a structured set of DC divisions and UPS-backed load groups, including 3 independent safety class 1 emergency DC divisions. Battery capacity and external flex connections, so we can connect an external generator if needed. Support extended coping capability, and overall, the system is designed and divisionalized to maintain availability and reliability of the safety functions without disruptions to plant operations. So our main generator line is here, connecting to our step-up transformer to the grid, as well as our reserve auxiliary transformer on this side, or station service transformer to feed station loads or to help during startup. And then the standby diesel generators A and B are shown here. Now, I wasn't permitted to share our exact Darlington nuclear site layout right now, and as well as with multiple units, some things are still being decided upon. But the standard information on the BWX site layout is still very relevant, where you have our control and service buildings, a reactor building here in the middle, with the turbine building on the other end. what this might be missing is that there could be some auxiliary buildings along there to hold certain, like the standby diesel generators or other or a chem lab might be found surrounding the main body or the main buildings here. Some comments on the safety strategies. So the framework starts with clear definitions. Hazards can trigger incidents, which can create postulating incident events, postulating initiating events that lead to event sequences and which are evaluated across different plant states, categorized by the frequency into anticipated operational occurrences or design basis accidents and design extent conditions. Safety assessment then combines hazard evaluation with deterministic and probabilistic methods, including risk-informed, performance-based insights to generate design to analysis. These then create the requirements that are driven into the design requirements for different systems and different architectural levels. A little bit about the grid connection. So in Ontario, actually initially when we had started this project, we were kind of directed to connect to we were planning to connect to a 230 kV system. And then we, in collaboration with Hydro One, the transmitter, and the ISO, the system operator, the ISO recommended a connection to the 500 kV system and recommended that there should be reinforcements to the system in general, just certain additional lines to improve the grid's 500 kV system. So the ISO published a recommendation regarding connecting the SMRs to the grid. So from the BWX perspective, the switchover requirements are intentionally minimal and conventional, relying on just a breaker and a half dual bus arrangement and controlled access to any protection or controls relay houses. So currently the BWX is connecting to the 500 kV system to an expanded Bowmanville switching station, which also introduces kind of additional circuits going to other parts of the system closer to the GTA, the Greater Toronto Area as well. So we're working to develop the transmission line routing and path. We are next to the Darlington nuclear generating station, which connects as well to Bowmanville. So they're expanding Bowmanville to connect the SMR as well as other lines in Ontario. I'll kind of proceed ahead here. So the BWX construction plan is structured to control schedule and cost risk through repeatable modular installations, validated construction methods, and modern planning tools like a digital twin or a 4D building information system. The strategy emphasizes doing underground and site enabling work early, especially circulating water and trenching and piping to keep the main construction footprint clear. The reactor building shaft is treated as a key sequencing element with options for conventional excavation support or a slurry diaphragm wall approach that can stabilize soils and potentially allow adjacent foundation work in parallel. The reactor building is built bottom up using modular structural elements with flexibility to either top load major equipment during floor placement or to defer installation and avoid supply chain delays. This is a bit of a breakdown of the DPSE, diaphragm plate steel plate composite foundation, which is how the reactor building is built. And as mentioned, some of these components become modules in the fabrication site. They're brought to our pre-assembly building where they're assembled into the full ring, and then they're lifted into the reactor building. And then the connections are completed there. So just some updates from today. So the heavy lift crane, which is going to lift the reactor building base mat and lower it into the the shaft building, is complete. So it's about a 94-meter tall train. It's the largest crane on site, and it's going to be prepared to lift a 2 million pound base mat foundation for the reactor building next month. The base mat assembled is mentioned is the DPSC, and it's in the pre-assembly building, ready to be lifted. Here we're showing some of the tunneling for that CCW, the condenser cooling water tunneling that goes into the lake. And as well, this is an image from the bottom of the reactor building shaft. There's been the site establishment team recently celebrated the completion of 2 warehouses and a fabrication building, as well as some progress has been made on our control building, turbine building, and the condenser cooling water pump house structure. Additionally, just as I mentioned earlier, just this week, OPG has officially submitted our license to operate application to the Canadian Nuclear Safety Commission, which marks a huge step in towards commissioning and future reactor operations. This is the first LTO submission for OPG in over 35 years, and the first for Canada in terms of SMRs. In parallel as well, the CNSC has cleared regulatory hold point 1, which was provided to us as part of our license to construct, which is a key regulatory step that allows the base mat installation, so the foundation of the reactor building, to move forward at the end of April. With this cleared, the project is not only authorized to begin foundation placement, but also start civil construction of the reactor building, including the structure, internal civil structures, and internal systems and components. There is a RHP2, so a regulatory hold point 2 regarding the reactor pressure vessel that's still being progressed. I believe this is a video. Oh, yep. Just a little scan over the site here. As we kind of pass over the reactor building shaft, these plots here are the destined locations for units. Well, we're looking at units 3 and 4, and units 2 is currently a laydown on the right there. And as we kind of get further, you see here the fab shop, the warehouses, and future administrative building. Transmission lines are not shown here, but they would be to the left of this as well. I know we're kind of coming short on time here, but I just want to highlight a lot of the IEEE guides and standards are being adhered to or pursued for a lot of the electrical and INC designs, as well. There's other designs as well, which touches on environmental qualification, operating performance, cable raceway systems, emergency and standby power, freeze and cathodic protection, as well as our preferred power system. So thank you very much. I may have taken over too much time here, but thank you for the opportunity. I'll happy to answer any questions as much as I can as well.
Thank you very much, Michael. That was a superb overview of this groundbreaking project in Ontario. And so thank you for taking this big 360 view of the project to get us all up to date. We do have a few questions. We may go a couple of minutes over, Ipsitar, if that's okay. One question was regarding the control system. So what kind of control system are you actually using for the WX?
So maybe I don't know if it can be clarified, but we're like there's a DCIS, so distributed control and information system, that kind of builds that whole network that I was showing. Maybe I'll try to grab that, but so we're entering into kind of a digital led control systems. However, some of the safety class 1 or the emergency control systems are still they still have hardwired connections, as well as providing information through the unit data highway. In terms of the component or the controls itself, for the safety class 1 systems, we are using a NUMAC, so NUMAC controller. And I don't remember what NUMAC stands for. I think nuclear unit measurement and something else. And then for so the mid-level and lower level safety class systems, we're using Mark 6 and Mark 6 ES controllers. So those you can search those up. There's a lot of information about the Mark 6E and then the new Mac
Okay.
systems.
Thank you very much. And another question, totally different, is relates to the licensing. So, licensing is, of course, now considered in the other countries that you already mentioned.
Mhm.
So, do you see that there could actually be the possibility of an international licensing system for SMRs in the future? Do you hear anything in that respect?
Um, I think I had some notes here. There is collaboration, I will say. I don't know about in a standard licensing approach, but there is collaboration with, for sure, CNSC in Canada and the US NRC. So they
Mhm.
do work together to kind of help reduce the burden and kind of provide a more efficient path. I have heard that there is possibilities of the CNSC working with any regulators in Europe as well, but I'm not privy to any kind of
Okay.
developments that they've made there, but I know that they have the right, it's within their kind of ability, and I think it's something that they pursue is to collaborate together. But I don't know if they've come to some formal standardization or agreement of such.
Okay. Thank you. And there was some chatter in the chat or in the Q&A about LP turbines. Do you also all have LP turbines?
Yeah, so there's one high pressure turbine and two low pressure turbines. So that's the arrangement is there. Yeah.
Okay, and another question, so they all go all over the place in different directions, is
Okay.
about waste heat. So are you also considering the collection of excess heat for different purposes as opposed to just cooling?
Yeah, so for the Darlington nuclear project, we are not looking at other uses for what we call waste heat. I will say the BWX 200 does s- offers that. Now we haven't kind of pursued that in our application due to our specific location and maybe some of the heat values. It may have not made sense. It's something that we looked at, but yes, our as I mentioned, kind of our goal is base load generation,
Yeah.
some maneuverability.
So, talking also about cooling, so how far away from, like you mentioned, the lake, Lake Ontario, how far away from the lake is the facility actually? Like, how far does the water have to be pumped?
Not very far. I don't want to make up a number, but it's under like it's in 200, less than that meters. It's we're on um the the edge. If you search up the Darlington Nuclear Generating Station, we're right next there, and it's right on the water itself. So it's a very short distance, but don't have that offhand. But yeah, we're on the water.
So the cooling water, at what temperature would it be returned to the lake?
Um, Maybe I could take that back and pass that. I just don't want to give a wrong number, but I know we make sure that it's not brought to such a high, or it's not a high temperature that would have any impact on the lake as part of our environmental assessment to ensure that it meets that the value we guaranteed there. But I'll take it back if that's okay.
Yeah, thank you. Um, cool. You talked about the grid connection. So, are there actually very specific requirements associated or challenges with connecting a nuclear power generation plant into the grid?
So there are specific requirements. The challenges. So in Ontario, we work with the ISO, the system operator, which has, as part of their marker rules, they have a chapter dedicated to grid connection requirements. Um, and they get those requirements kind of passed. Some are ISO specific, while some are passed along from NERC and NPCC. So NPCC is their regional authority. Um, there, there are possible challenges in terms of like well, one, you have to work with your transmitter to make sure that your the complete megawatts and the amount of infrastructure needed that needs to be built from the from the generator side and the transmitter side needs to be able to accommodate that. Um, Sometimes there are requirements regarding frequency response, and that changes how fast a generator changes the megawatt output in the event of a frequency divergence. So that is something that kind of any nuclear generator looks at, and how fast they can change their megawatt output to match any grid frequency changes. But as far as kind of voltage and stability and in terms of outage coordination, there are challenges, but those are all can be worked through. So um, as well as diesel generators as well, you have to be careful as to depending on their size, how they might impact the grid if you're using them during testing while connected to the grid.
Mhm. Yeah, thank you. So I've like people are still generating questions. I will try to get a few more through. So there's a question about the cost per megawatt demand. Would you have an estimate for that for the SMR?
So let me. I was looking to. I know we have shared kind of um, the total project costs, or
Mhm.
the estimated total project cost of $20.9 billion. The localized cost of electricity, um, I don't have an exact value right now to share.
Okay. Um, Once you get to the four SMRs, do you have specific plans for like routine maintenance um, processes and schedules and so on? Like how do you handle the maintenance? What are the out times, down times?
Yes, here 1 second. So yes, we are that's something OPGs is leading in a big way regarding our future operations and maintenance procedures and plans. Um, the outage assumptions that we've been looking at are 10 to 15 day outages for refueling, and 25 days, a major inspection outage, which would last about 25 days for about every 10 years. So refueling outages, we believe, again, those are 10 to 15 days every 12 to 24 months. It depends on how we structure them and plan. Um, and then larger major inspection outages should be about 25 days, and those are targeted about every 10 years or around that frequency. I
Okay,
think with unit one, once that's come off, I think the plan is to have an outage after 1 year of unit one to just assess everything and to make sure things are all operating as they're planned, and then continuing on with either a 1 or 2 year cycle.
okay, thank you. Then another question was regarding the use of borated water. So what is the
Um,
use?
is that like a boron injection or sorry, did
That I
I?
cannot tell. Maybe this was a question from Jacob, and maybe you can post a follow-up question, Jacob.
I will say there is a kind of a boron injection system, which is a bit of a last resort shutdown
Mm.
backup that provides a diverse way to make a reactor subcritical if control rods can't shut down, or if there's an issue with the isolation condenser. So this is kind of like a last resort emergency action if we're talking about boron injection. But yeah.
Okay, so most likely you have answered the question. So here's a bit of a challenge, and says like we have just built a 157 megawatt solar plant in one person's neighborhood, and the process took less than 2 years from planning to commissioning. So why bother with the complexity of an SMR if it's so easy to put solar generation in place?
So I would say I think different areas or in different economies have different best solutions, and I'm not sure where our friend is commenting from.
Yeah.
I haven't thoroughly studied solar generation in Canada, but I know that it has some challenges compared to other places in the world. Um, I think what we see here and what we've seen with our OPG's Darlington facilities built um, in the 80s that again they've now been renewed for another 30 years. So there's a long life to a lot of these nuclear plants when we can work at them with great care. So I think what we see here is yes, maybe a big investment up front, but a long-term a payout when they've been operating for so many years, and they do provide a reliable source of power, right? So our nuclear assets most of the time when if there's no outages, they're online at full load for hundreds of days at a time without any changes. And I think you might need a mixture of both because again, your grid can't be changing as much as your solar power provision, right? You need stability, base load generation.
Yeah, and actually, with respect to the baseload generation, so you said you can provide between 50 and 100% of the nameplate power.
Mm-hmm.
You can drive it up and down. How fast, like how reactive would the output be? How fast can it be changed?
So so yeah, the comment there is that the the BWRX can move from 100% to slow down to 50% and hang there for about, I think, several hours before it has to go back to 100%. Just and again, because as you make power output changes, you change how the fuel is being used, and how fuel is used changes how your fueling cycles, amongst other things. So I think my understanding is that it is rather is a bit slow compared to maybe some other systems where this moves about 1.5 to 2 megawatts a minute in reduction. So that is kind of the sorry, that's not to say that's how fast it can totally move, but that's our preferred path will be that it slowly moves down like 1 or 2 megawatts a
Okay.
minute. There are ways to rapidly move down in the event of a trip or in the event of certain actions using kind of a turbine bypass system that we talked about to help there to reduce a jump by like possibly 25% power output but rather quickly to support those environments. But the preferred way is kind of slowly move down and up.
Okay. So could you state once more when you expect the first unit to be online?
I believe our commercial commercial date for operating is early 2030, Q1 of 2030. We
Okay.
do have a energization date planned for 2028, so that's when we can backfeed from the grid. So a lot of our electrical systems should be in place by that, possibly late 2028, but that is the target.
Okay. Thank you. And so a couple more questions. Like, would comparing the BWR technology and the PWR technology, is there a significant difference in generating cost?
To be honest, I wouldn't be able to answer that well. I'm not too familiar with PWR and haven't really compared them, but I believe there's a lot of information that can be read on
Okay.
that.
Okay. And so the other question is here regarding monitoring the heat exchanger. So are you actually continuously monitoring heat exchanger effectiveness?
I bel is I don't know the actual monitoring system about the heat exchangers, but there is IO mapped to some of the temperatures measurements at different locations, so it should be monitored, but without
Okay.
kind of going into the details of the system, I don't know.
Okay. And the another detailed question is around what the temperature of the steam that reaches the turbine. What temperatures are we talking about?
Um, Let me 1 second.
And we're getting on to 1:15, so we're probably getting close to the last question.
Okay.
If there are furthermore, like I haven't been able to give you all of them, but if people want to follow up, I can post an address in the email or Ipsita can, and you can get in touch with us and we try to answer further questions.
Sorry, yeah, that's totally fine. Yeah, the core inlet temperature is 270 degrees Celsius and the outlet temperature is 208 degrees Celsius. So around that. I was thinking pressure, but the nuclear steam supply pressure, operating pressure is 7.1 megapascals.
And just thank you. And one last question then. You talked about the fab facility for some of the components and so on. So is the intent that the fab facility would also then provide parts for a potential SMR built in New Brunswick, for example?
The immediate plan for the fabrication building on site is kind of to feed the DNNP. Now, after
Yeah,
Unit 4 is constructed, I imagine OPG's kind of been working with other utilities to support them too if they seek out the same technology. So I don't know if specifically the fabrication building on site is, but I imagine some of the supply chain or the fabrication yards maybe off site that OPG is working with. Yeah, we'd work with them to help any other utilities as well.
yeah. Yeah, there seems to be some very constructive collaboration between Ontario, New Brunswick, Saskatchewan, Alberta, and I don't know whether any other provinces, but there seems to be a lot of sharing going on today. So I think,
Yes, I think there is a memorandums or letters of understanding or working together agreements
yeah, yeah.
with all those utilities you mentioned. So exactly, or provinces you mentioned. Yeah.
So with this, I would like to thank you very, very much, Michael. This was a terrific presentation. I'm sure a lot of work went into the preparation because you took us really 360 around the site, including a video of the site. That's really fantastic. And I invite our guests to pose further questions if you have them. And then we can hopefully address them either directly via email or see whether we can identify another channel to do so. So thank you very, very much. Thank you for everybody who joined us. Um, I saw some really nice comments on your presentation in the chat. So people have been thanking you and maybe you've seen it yourself. So again, thank you very much. Thanks for putting this together. And we'll hopefully get an update from you maybe in a year or so to see how we have progressed and what's new and exciting about SMR technology at Darlington and potentially other developments. Thank you very much.
Thank you.